control 180 lines. CKV1, 2 and 3 be assigned to the odd lines. CKVB1, 2 and 3 will be assigned to the even lines. We find the terms CKV1, CKV2, CKVB1, CKVB2 in Samsung panels, but other companies use other terminology to designate the various clock signals. In LG panels, the terminology used is CLK1, CLK2, VGH odd, VGH even. In the AUO panel is used HC1, HC2, LC1, LC2. HC is an abbreviation of high clock and LC low clock. The level shifter can be located both before and inside the gate driver. Here it will allow to transform the digital signal VDD and VSS into VGH and VGL. If the output of the logic circuit is at a high level or 1, it is translated to VGH. If the output is at a low level or 0, it is translated into VGL. The last step in the gate driver, before the VGH and VGL voltages reach the TFT transistors, is their passage through a buffer. The latter is a voltage follower circuit whose purpose is to separate the circuits present in the gate driver from the TFT transistors and storage capacities that are inside the panel and constitute the load to be supplied with voltage. We now arrive at the OE signal, which is a contraction of the words output enable. We see that this signal is placed downstream of the output of the shift registers. The role of the OE signal is to control the activation time of each output. Here is the reason. In this illustration, in green is represented the voltage VGH which feeds the gate of transistors placed on the same line. This conductive line is not perfect because of the parasitic effects, which are the resistance of the conductor and the presence of a parasitic capacitor between gate and source called here CGS. The resistor and the parasitic capacitor constitute an equivalent of RC circuit low-pass filter. The electrical pulse VGH that we call gate pulse must travel a certain length from left to right. With the parasitic effects of conduction, the VGH signal will undergo a distortion on its rising and falling edge. We see the signal at the beginning of a line is not exactly the same at the end of the line. This distortion can be seen especially with large screens for an obvious reason of the longer line to cover. This defect of conduction has consequences on the quality of the display. On this diagram is represented the progression of the display of the image line after line. At the time of the activation of the first line, the data of the image is delivered to the corresponding line and with the adequate time. Then it is the turn of the second line to be activated with VGH while the previous line is switched off with VGL. The coordination process between the lines and the data will continue successively until all the lines are scanned. It is the T-Con board that ensures the coordination between the activation of a line and the delivery of the data to the corresponding line. As a reminder, T-Con is an abbreviation of timing control. In practice, because of the parasitic effects of conduction, the VGH signal undergoes a distortion and a shift in time. Line 1 will not stop at the desired time, and the data which are intended only for line number 2 will also be displayed on line 1 since it is not stopped. This will create an abnormal display of the image. This phenomenon is called crosstalk to say that the data from line 2 will also reach line 1 since it is not yet stopped. In this animation you can see the coordination that exists between a line that is activated and the data that reaches it. After receiving the data, if line 1 does not stop in time, this is what happens. The data from line 2 will also be delivered to the first line, but this data was not intended for it. This is the phenomenon of crosstalk and leads to an abnormal display. To correct this crosstalk problem, we introduced the OE signal for output enable. When this signal is at high level, it stops all the lines that are active. When unfortunately the operating time of two lines overlap, OE allows to block this zone. This prevents the data from being misdirected. This is equivalent to controlling the operating time of each line. The width of the OE pulse is variable and only acts on the lines that are active at the same time. The XAO signal is a signal that allows to detect the extinction of the screen. This signal has been added to deal with the problem of image retention even after the screen is turned off. when the screen is on, the XAO signal is at its high state. When the screen is turned off, it goes to its low state. This causes all the TFT transistors to be turned on at the same time, and it allows all the capacitors of the screen to be discharged. This is why the XAO signal is assigned a reset function. We see on this chronogram, although there is an OE pulse, there is no action on the state of the line because XAO is higher than OE and does not allow it to block the operation of the TFT. As another name for XAO, we can find on the datasheet the name XON. On the electronic side, XAO consists of a voltage detector. It monitors the VIN voltage. When the latter falls below a certain threshold, as when the screen is turned off, XAO emits a reset signal. In this assembly, there is a voltage comparator and a MOSFET configured in open drain because its source is connected to the ground. This diagram shows the various circuits that we have seen. At the beginning, there is the shift register with the different inputs, CPV or CKV, STV or SVIO and SVOI, LR and UD, followed by the logic circuit composed of NAND gate, logic voltages VDD and VSS, and the signals OE, XAO or XON. Then comes a level shifter which translates the digital signal into an analog signal made of the voltage VGH and VGL. Last step, VGH and VGL pass through a buffer to be distributed to the TFT inside the panel. We arrive at the end of this video with this animation that summarizes the mode of operation and control of the pixels by the gate driver through the various electronic circuits that constitute it. Goodbye and see you soon.